Okay, so I just wanted to talk through this idea of what an exponential is. Now, a lot of you will have heard of the word exponential before, okay? And typically, we talk about an exponential in relation to either growth or decay, okay? Now, actually, I'm going to focus on the growth situations, the things which are getting bigger, because if you can understand the growth situation, then you'll understand the decay situation, because it's just simply the negative of growth. Okay, so it's just literally growth in the other direction. Okay, so let's first of all understand what an exponential function actually is. All right, so well, actually, first of all, I'm going to talk about different types of growth functions. So let's suppose, for example, we have a linear growth. Okay, so linear growth situation. Now, just for the sake of argument, I am going to sort of introduce a couple of variables. So I'm going to say y is the amount of money which I have. Okay, so the amount of money. Okay, and I'm going to let x represent my time. And I'm just, for the argument's sake, I'm just going to represent time in years. Okay, so here we have two variables. X represents the time, and y represents the amount of money I have at any particular point in time, after 2 years, 3 years, 4 years, whatever. Okay, so let's first of all talk about the linear growth situation. So here is the equation. So I want to come up with an equation which will basically say, right, if my money is growing in a linear way, how can I work out how much money I have at any particular point in time? So let's say, for example, that my growth equation, my money equation, is just y, the amount of money I have, is the same as just taking my year, what year I'm at, and just multiplying it by 2. Okay, so 2x. Y equals 2x. Okay, so this is a linear growth situation. So let's, for example, just draw ourselves a little table. Okay, so let's suppose I have the year which I'm at on the left column and the amount of money which I have in the second column. Okay. So here we go. Let's start at year 0. So in other words, when I first put my money in my bank account, let's say. Okay. So how much money will I have in year 0? Well, I just simply stick 0 into this equation up here. So 2 times 0, that means that I have £0. All right. All right. So let's have a look. After 1 year then, so x now equals 1. How much money will I have? Well, if I use this equation, the amount of money which I have will be equal to 2 times whatever year I'm at. So 2 times 1, which of course is 2. Okay. Then after 2 years, how much money will I have? Well, it's going to be 2 times 2, so 4. Then after 3 years, how much money will I have? Well, 3 times 2, that's 6. And then after 4 years, let's stop after 4 years, I'm going to have, well, £8. Okay, so can you see that for every increase in this direction, so for every year that I move up by, can you see that what's basically happening with my money is I'm just increasing by 2. So I'm just increasing by 2 each time. Now this is what we call a linear situation because I'm going up by the same amount for every increase in the years. Okay, so I'm going up by £2. In other words, my change is constant. That's what we call linear. Okay, so a linear growth situation is when my growth is constant. Okay, so my constant growth. In other words, I'm going up by the same amount each time. Now if I was going to plot this, fairly obviously, I would have a graph that looks something like this. Okay, so y equals 2x. In other words, for every year that I move across by, I move up by £2. So year across, £2. Year across, £2. Okay. So in other words, the rate of change of my growth would be constant. And you can verify that because if you differentiate this, okay, that should be equal to 2. Therefore, my rate of change is constant. In other words, it's going up by £2 every single year. Okay, so that's linear growth. Now let's look at a slightly different type of growth. Let's look at polynomial growth. Okay, so polynomial growth is a little bit more interesting. Okay, so instead of say taking y equals 2x, let's say for example the amount of money I have is given by some power of x. Okay, so let's suppose x squared, for example. Let's just switch the positioning of the 2. Okay, so let's have a look now at what happens with every year. So let's go 0, 1, 2, 3, and 4. Okay, so I'm just going to consider the first 4 years. Well, fairly obviously, at the start, I'm going to invest, well, 0 squared, that's going to be £0. At the start, I have nothing, okay? Then after a year, well, I just stick it into this equation. So 1 squared, that gives the amount of money, so that's going to be 1. After 2 years, 2 squared is 4. I'm going to have £4. 3 years, 3 squared is 9. I'm going to have £3. And then 4 years, well, 4 squared is 16. Okay, so can you see that it's a slightly better situation than what was happening up here with my linear growth? It's growing slightly quicker. Okay, and in fact, what am I moving up by? Well, from year 0 to year 1, I'm moving up by £1, so I've got £1 more than what I had. From year 1 to 2, a year later, I now have £3 more. From year 2 to 3, I now have 5. From year 3 to 4, I now have 7. Okay, so can you see that for every increase in the year, it is still a kind of linear increase, but it's kind of buried underneath. Okay, so it's not changing by the same amount each time, but if you look underneath, it is a kind of linear increase. And in fact, you can verify that by looking at the rate of change. So how quickly am I growing? Well, if I differentiate this, I would just get 2x. In other words, the change is growing in a linear fashion, which is what you can see over here. Okay, so in fact, if I just sketch this, you should end up with something that looks like this. Okay, so would you be happy this is now a non-linear type of growth? Okay, non-linear, and we've chatted about that before. Okay, so linear growth is simply where the rate of change is constant each time, but now the rate of change will be different depending on which point we look at. Okay. Now, let's come back to this idea then. So how does exponentials fit in with this? Well, exponential growth is a brand new type of growth that's even faster than any other type of growth that we've seen. So linear growth or polynomial growth, okay? So exponential growth is simply where we flip these two things around. So instead of having the time being raised to a constant power, we do it the other way around. We say that the constant will be down here and the power will be what time we're looking at. Okay, so y equals 2 to the power of x. So okay then, let's plot this. Let's see actually what's happening here. Okay, so we'll do 0, 2 to 4 years. So 0, 1, 2, 3, 4 years let's look at. And let's just see what happens at each particular year. So at year 0, we're going to have 2 to the power 0, which is just 1. All right, and let's have a look. So year 1 then, year later, we're going to have 2 to the power of 1. The amount of money which we're going to have is £2. Okay, so already we're looking quicker than either of these two growths. Okay, then let's look at 2 years. Okay, so 2 years, we're going to have 2 to the power of 2. That's going to give me £4. Okay, and then 3 years, well, 2 to the power of 3, that's going to be £8. And then after 4 years, we're going to have 2 to the power of 4, which is 16. Okay, so at the moment, there's kind of not much difference here. But can you see that if we keep going with this, exponential growth is going to far sort of exceed, pass the polynomial growth. In other words, it's going to grow much quicker than the polynomial growth after time. Okay, but let's actually look and see what's happening here. So every single year, can you see that what's effectively happening? We are doubling the amount of money. We are doubling the amount of money. So this is different to either of the two growths that we've looked at before, so linear and polynomial, where we're moving up by a constant amount each time. Okay, so it's either a constant amount or it's a linear sequence which is buried underneath that. Okay. With exponential growth, you're no longer moving up by adding an amount each time or adding a sequence each time. You're now doubling each time. You're now doubling each time. So in other words, this is going to grow much, much more quickly than any other type of growth that we've seen before. So it becomes really, really rapid. Really, really rapid. Okay. So what? Who cares? So exponential growth, it's a type of rapid growth. And it's specifically a type of growth where you're multiplying by the same amount each year. Now, how do we know how much we're multiplying by each year? Well, that's just simply given by whatever this base is down here. So at the moment, this base is 2, which tells me that I'm doubling for every single time period. Okay? If I change this for y equals 3 to the power of x, for example, this would now tell me that I'm tripling every time period. If I change it to 1,000 to the power of x, this would now tell me that for every time period, I would be multiplying by 1,000. Okay, does that make sense? So this base down here tells you what you're multiplying by for each time period. Okay, what you're multiplying by for each time period. Now, if I change the function slightly, so if I change it, for example, to be y equals not 2 to the power of x, but 3 times by 2 to the power of x, okay? All that will basically change, you'll still be doubling every single time period, but all that will change is what you start with, okay? So in this case, I'm proposing that this number here tells you that you should start with £3 and then double for there every year after that. And you can verify that very quickly just by drawing yourself a table of values, okay? So now, for year 0, you'd stick 0 in here, so you get 3 times by 2 to the power 0. Well, anything to the power 0 is just 1, so you get 3 times 1, so that's £3. Now you compare that to what we started with over here, okay? We started off with £1 because there was effectively just a 1 hiding in front of that, okay? So effectively, the number which we have here tells you what you start with, and then you should just double or triple whatever this number down here tells you to do every year after that. So for example, 1 year later, you're going to have 3 times by 2 to the power of 1. 2 to the power of 1 is 2, times that by 3, you're going to get 6. Then after 2 years, you can verify that's 12. 3 years, you can verify that's 24. And then 4 years, you can verify that's 48, and so on. So you're still going to multiply for every 2 years, every year after that, multiply by 2 for every year after that. It just so happens that the number we start with is given by that instead. Okay? So exponential growth is a really, really rapid type of growth. So, what can we do with this? What if we wanted to work out the rate of change? The rate of change. Well, by definition, because you're just doubling the amount which you had at the previous year, the rate of change should change according to how big it is. Okay? The rate of change should change according to how big it is. In other words, the bigger the population is, or the bigger the amount of money which you have in your bank account is, okay, the more it can grow by, okay? The more it can grow by. So, in other words, another way of expressing this same statement, the bigger something is, the faster it can grow by, is to say it's proportional to, okay? So the rate of change, remember dy by dx, that's just simply the rate of change, how quickly something is growing, is proportional to the population size, or the amount of money which you have. Okay, so y is the amount of money which you have, and dy by dx is the rate of change. Okay, so the amount. And this symbol here just simply means proportional to. So in other words, if size goes up, if you have more money, okay, the rate of change will also go up. In other words, it can grow even faster. Okay. Now, if I change this situation slightly, so if I go back to money, okay, the more money which I have in my bank account, the faster I will grow. That makes sense, right? Because if I just start with £1, or if I just have £1 in my bank account, according to this rule up here, or the 2 to the power of x rule, basically just says just double for every year. So 1 year later, I'll just end up with £2. So in other words, the increase is only £1. Whereas if I start off with, say, £1,000 in my bank account, then a year later, according to y equals 2 to the power of x, I should have double the amount. So therefore I should have £2,000. So in other words, my increase is now £1,000. Okay? So in other words, the rate of change changes according to how much you have, or how it changes according to your size. Okay? So it's a really fundamental idea of exponential growth. Okay? The bigger something is, the faster it will grow by. Now, a really nice illustration of this is through like a snowball rolling down a hill. So let's imagine this is like a cross section of a hill, okay? So at the top of my hill, I start off with a really small snowball, so maybe a snowball that fits into the palm of my hand. Then I roll it down the hill, so I roll it down the hill. Now, are you happy that as it rolls, the surface area will increase, okay? Because it picks up more snow, which means that it can grow even faster because there's more surface area for the snow to cling to. Okay, and when it gets down here, there's even more surface area for the snow to cling to, which means it can grow even faster. So in other words, the snowball can change, or can grow, even quicker the bigger it gets, because there's more surface area for it to change to, for it to cling to. So therefore, it follows this idea here. The rate of change is proportional to its growth. Now, another way of writing this, if I wanted to change it to an equation, is to say that the rate of change, dy by dx, is going to be just some multiple of your population. Okay, so k here is just some multiple. Okay, it could be 3, it could be 4, it could be 2, could even be negative if you're talking about negative growth or decay. Therefore, k is just simply some multiple of your population. Okay, so as an example, and we'll talk about this in a little bit more detail a little bit later on, if I start off with y equals 2 to the power of x, I happen to know, and I'll just tell it to you for the time being, but eventually you'll be able to prove this, that the derivative, the rate of change, is just the natural logarithm of 2, so we'll talk about logarithms as well, of 2 to the power of x. Okay, so there's my y. There's my y, there's my population size. And it's just some constant, ln2 is just a number, it's just some constant of this. So in other words, this condition holds. So in other words, the rate of change is proportional to how big the population is, how big the amount of money you have in the bank account is.